Small Orchestrator model outperforms GPT-5. NVIDIA has released Orchestrator 8B, a compact 8 billion parameter model designed specifically to coordinate complex, multi-turn agentic tasks by managing a diverse set of expert models and tools. According to NVIDIA's claims on Hugging Face, the model achieves a score of 37.1% on the Humanities Last Exam (HLE) benchmark, reportedly outperforming GPT-5's 35.1%, while being approximately 2.5 times more efficient. The community reaction has been a mix of enthusiasm and skepticism. As one commenter explained, "This isn't a chat with my buddy LLM. It's designed to be a lightweight, fast task coordinator that organizes subtasks and makes tool calls to downstream operator agents, allowing larger, slower models to do the actual work asynchronously." The model is built on Qwen 3.8b and trained with a combination of a large MIT licensed dataset and a small proprietary tool-scale dataset of about 4,000 records. The licensing situation has drawn pointed criticism. NVIDIA used an Apache 2.0 base model and a mostly MIT licensed dataset, then added a proprietary fraction of a percent of data and released the whole thing under a proprietary license. As one commenter put it, NVIDIA can't contribute a meager 4,000 records to open source. Why aren't they contributing? Defenders note this is technically permissible under MIT Apache 2.0 terms. And the good news is that if those 4,000 records can be replicated or distilled from the model, the open source community could create their own version. Some users have already begun discussing using tools like Deep Fabric to replicate the dataset structure. Not everyone is impressed by the benchmark claims, with one commenter flatly stating, "It's good, but it's not GPT-5 level good, not even close." Others remain wary of NVIDIA's track record with models, noting past disappointments. Still, the architecture itself, a small model sitting atop an agentic stack, is widely seen as the future for real AI products beyond simple chatbots. SFT from scratch reveals debugging realities. A detailed write-up on building supervised fine-tuning, SFT, from scratch, loosely following Stanford's CS336 Assignment 5, has surfaced on Reddit, offering a candid look at the gap between writing training code and making it actually work. The author reports spending more time debugging gradient instabilities, wrestling with VLLM integration, and diagnosing confusing loss curves than writing the actual SFT logic. Two main experiments were conducted. Reasoning SFT on Qwen 2.5 Math 1.5b with math reasoning traces, and Instruction SFT on Llama 3.18b with UltraChat 200K and Safety Llama. The results are instructive. For reasoning SFT, training on all 4,800 examples, including incorrect reasoning traces, yielded 42.1% reward accuracy, but filtering to only correct traces, 3,600 samples, boosted accuracy to 52%. Running a second epoch on the filtered set reached 53.4%. The takeaway: data quality matters more than quantity, and models learn wrong patterns from wrong examples. For Instruction SFT, GSM-8K accuracy doubled from 16.4% to 32.7%, safety scores jumped from 62 to 78%, and AlpacaEval rose from 1.6% to 5.3%, while MMLU remained essentially flat at 58%. Several debugging lessons stand out. Per token versus sequence level loss normalization made a significant difference. Longer sequences contributed disproportionately to gradients, causing instability until the author switched to dividing by actual response tokens. VLLM integration proved tricky across versions, with API changes and torch.compile wrapping the model under OLMo. BPE tokenization boundaries also caused headaches. Tokenizing the prompt separately versus the full sequence gives different boundary tokens, requiring the last prompt token to be dropped before masking. All code, datasets, and checkpoints are publicly available for those who want to replicate or build on this work. Next lands in LM Studio. The LM Studio beta now supports Qwen 3.80b Next, a significant addition for local LLM enthusiasts seeking to run large models on consumer and workstation hardware. Early testers report mixed but promising results. One user with an AMD W7900 48GB card achieved approximately 20 tokens per second at a 130,000 token context, noting almost no performance drop as context filled. Another running an NVIDIA RTX Pro 6000 Blackwell Workstation Edition at full context with Q4KM quantization reported 19 tokens per second, though GPU utilization was only around 33%, suggesting optimization is still pending. The current llama.cpp implementation powering this support is explicitly labeled as correctness only, with speed tuning and broader architecture support to follow in future updates. Several users observed high CPU usage even with all layers offloaded to GPU, which the developers acknowledge is a known limitation at this stage. Some report crashes when loading certain model sizes, and performance varies widely depending on hardware configuration. For Mac users, MLX versions of Qwen 3 Next have been available for weeks, allowing those with shared RAM to run the model without waiting for GGUF runtime support. The broader point, local inference for truly large models is becoming more accessible, but early adopters should expect rough edges. New tools tackle RAG debugging and memory. Debugging retrieval augmented generation. Pipelines has long been a frustration for developers. When an agent gives a weird answer, it's often unclear whether the fault lies with the wrong chunk, a distant embedding, or stale data. A new open-source project addresses this by providing a real-time RAG visualizer for pgvector, a popular Postgres-based vector store. The dashboard displays the input query, how text is chunked and vectorized, and exactly which database rows matched, along with their similarity scores. A recency decay feature adjusts rankings so that the agent doesn't pull up perfect matches that are 3 months old and irrelevant. The underlying logic uses a weighted score, 80% vector similarity, 20% recency. The code is Node.js/TypeScript, currently using OpenAI for embeddings, but with plans to swap in OLMo llama CPP for fully local operation. On the memory and orchestration front, a new local MCP, Model Context Protocol, hub and memory engine for OLMo is seeking beta testers. The project bundles multiple MCP servers, a SQL-based memory server with vector store, graph, and layered memory, short-term, mid-term, long-term, an AI gateway connecting LobeChat OpenWebUI Anything LLM with OLMo and tools, and modules for sequential thinking and validation. Everything is Dockerized and runs entirely locally with no external cloud dependencies. The developer reports a lightweight footprint, 300 to 600 MB RAM per service, minimal CPU usage, and no GPU requirement for the framework itself. The goal is a system that stores real memories, extracts facts, links knowledge as a graph, auto-routes MCP tools, and supports multi-LLM orchestration. Feedback is being solicited on memory quality, speed, and stability. Section Developer Tools for Codex and OpenWebUI. For developers working with OpenAI's Codex, a new terminal-based utility called Recall offers a snappy way to full-text search past conversations and resume them directly. The tool is installable via Homebrew or Cargo, and once launched in a project directory, users can type to search, navigate results, and press Enter to jump back into a selected conversation. The interface supports keyboard shortcuts for scrolling, copying session IDs, and toggling search scope. Community response has been positive, with users calling it freaking awesome and praising the clean UI. Meanwhile, a comprehensive GPT-4 405.15 Pro manifold for OpenWebUI has been released, bringing full responses API support, reasoning, image generation, cost tracking, and web search preview to the platform. The manifold supports pseudo-models with correct reasoning, effort settings, expandable thinking, done thinking UI sections, and encrypted reasoning persistence. Web search integration includes URL tracking, numbered citations, and a sources panel. Image support covers both input and output, with cost estimation even when WebUI hides the tool call. MCP tool support is included, automatically loading MCP servers into OpenWebUI. The motivation: OpenWebUI's current completions API flow doesn't fully support reasoning summaries, multiple tools per response, image generation, or accurate multimodality cost reporting. This manifold aims to bring feature parity with the official OpenAI playground. Vibe coding produces playable game in hours. A Reddit user spent about 7 hours vibe coding a highway shooting game called SigAlert, using Claude Opus 4.5, with only around 20 minutes of active prompting time. The project began as an emulation of Spectre VR, a 1991 Mac wireframe tank game, and evolved into a driving/shooting game set in Los Angeles. The technical stack, Three.js for 3D rendering, vanilla JavaScript for all game logic, and the Web Audio API for procedurally generated sound, was selected entirely by Claude, with no architecture planning or context management by the user. The game was immediately playable after each iteration, with bugs and features addressed through simple conversational prompts. The development process was described as dead simple. An initial prompt like, make a 3D wireframe game like Spectre from the 90s tank game that we can play in a browser, got the project started in 3 shots. Subsequent prompts refined camera behavior, added Easter eggs, and layered in soundtracks inspired by Pink Floyd and 80s bands like Chris and Cozy. The author noted that Claude never got lost the way other models did, maintaining architectural stability across revisions and producing good suggestions when asked. Community feedback highlighted the playable result, but also pointed out issues with camera movement causing motion sickness in some users. A reminder that AI-generated solutions may require human feedback to catch usability problems. The author later added selectable camera modes and a humorous glass stomach mode to address complaints. Qwen3VL rebuilt for learning. A minimal PyTorch reimplementation of Qwen3VL, the open-source vision language model, has been released as part of an ongoing TinyQuen educational project. The codebase is described as simple and easy to follow, aimed at developers who find Hugging Face Transformers code verbose and want to understand how multimodal LLMs work at a lower level. The project is inspired by Andrei Karpathy's NanoGPT and includes older versions of Qwen as well as DeepSeek R1 in the same repository. Community response has been appreciative, with requests for additional comments explaining implementation details, such as the second normalization for stability in routing and shapes for einsums that aren't typically covered in theoretical discussions. This kind of hands-on, hackable codebase serves as a valuable resource for those looking to move beyond high-level APIs and gain intuition for the internals of modern multimodal models. LoRa Repeater runs 5 years on D-cells. A project called LoRaTube demonstrates a remarkably simple approach to off-grid LoRa repeater deployment. House the entire device in a length of PVC pipe, power it with 18 D-sized alkaline cells, and expect roughly 5 years of operation. The design, created by Bertrand Selva, uses a supercapacitor buffered power supply and extends an antenna out the top. A basic repeater can be assembled in about an hour, and all source code and CAD files are publicly available. The approach sidesteps the cost and complexity of solar panels, charge controllers, and rechargeable power supplies, which can quickly add up and introduce multiple points of failure. The community discussion, however, raised substantial concerns about alkaline battery reliability over multi-year deployments, leakage being the primary worry. Anecdotal reports of brand-name cells leaking while still in the blister pack, or of batteries destroying expensive equipment, were common. Some commenters suggested positioning the battery holder at the lowest part of the tube to contain any leakage, while others recommended lithium cells for long-term reliability. Cold weather performance was also flagged as a potential issue. The broader lesson: sometimes cheap, simple, and rugged beats elegant and complex, but real-world durability depends heavily on component quality and environmental conditions. OpenGPT 4o image dataset advances generation and editing. A new large-scale dataset called OpenGPT 4o image has been introduced to address a critical bottleneck in AI-powered image generation and editing: the lack of systematic structure and challenging scenarios in existing training data. The dataset contains 80,000 high-quality instruction image pairs covering 11 major domains and 51 subtasks, constructed using a hierarchical task taxonomy and automated data generation powered by GPT-4o. For image generation, the taxonomy includes style control, covering artistic traditions, media, and illustration, complex instruction following, in-image text rendering, spatial reasoning, and scientific imagery, physics, chemistry, biology, engineering, data visualization. For image editing, 6 categories are defined: subject manipulation, text editing, complex editing, multi-instruction execution, multi-turn editing, global editing, and other challenging forms. The automated pipeline leverages structured resource pools and template-based generation to ensure controlled diversity and difficulty. Experimental validation is compelling. Fine-tuning leading models on OpenGPT-4o image yielded up to 18% improvement on editing tasks, Uniworld v1 on Imgedit bench, and 13% improvement on generation tasks, Harmon on GenEval. The authors highlight that the dataset addresses previously underexplored areas, including scientific imagery generation and complex multi-instruction editing. The methodology demonstrates that systematic data construction is key to advancing multimodal AI capabilities, and both the dataset and the process are being released as resources for future research. Deep research agents. Context engineering is king. Tavaly, a company focused on AI-powered research tools, has published a detailed post on the technical and philosophical lessons learned building a state-of-the-art deep research agent. Research agents are emerging as a top use case for AI, underpinning everything from writing and decision-making to coding. The challenge: building a software layer that enhances a model's runtime execution through context management, tool invocations, loop control, orchestration, and error handling, while absorbing performance gains from future model releases without handcrafted optimizations that become bottlenecks. The team's core insight is that context engineering, maintaining a clean, optimized context window over time, is the single most important factor for long-horizon research tasks. Tavaly's advanced search abstracts away the processing of raw web content, returning only the most relevant chunks from each source. Global state persistence and source deduplication ensure the agent is exposed only to fresh information, help recognize when the information scope is narrowing, and enable effective source attribution in the final output. A key technical contribution is the approach to token efficiency. Rather than propagating tool outputs through the tool calling loop, which leads to quadratic token consumption, Tavaly distills tool outputs into reflections, using the set of past reflections as context for the tool caller. Only at the point of final deliverable preparation is raw information provided. This reduces token consumption by 66% compared to open deep research, while achieving state-of-the-art on the frames benchmark. The team also emphasizes simplifying orchestration logic, leaning into autonomy, and exposing a small essential toolset. Fewer tools mean fewer failure modes. Evals are used for directional feedback, not as optimization targets. Intuition and careful agent trace monitoring often provide higher signal feedback than any single eval score. EmbeddingGemma sets new standard for small embedders. Google DeepMind has released EmbeddingGemma, a 308 million parameter text embedding model that achieves state-of-the-art results on the massive text embedding benchmark for models under 500 meme parameters. The model ranks first across all aggregate metrics on MTlingual v2, Mbep Code, and English v2 leaderboards for its size class, and ranks 8th overall on the multilingual leaderboard, 17 places above the second-best sub-500 meme parameter model. Performance is comparable to models nearly double its size, and the lead persists even when truncating embeddings to 128 dimensions or quantizing weights to 4-bit precision. EmbeddingGemma is an encoder-only transformer adapted from a pre-trained 300 mem decoder-only Gemma 3 model. The adaptation involves first creating an encoder-decoder model following the T5 Gemma recipe, then initializing EmbeddingGemma from the encoder. The model uses mean pooling over token embeddings, followed by linear projections to an intermediate and then target embedding dimension. Training employs 3 complementary losses: noise contrastive estimation with in-batch negatives and hardness weighting, a spread-out loss for quantization robustness and efficient approximate nearest neighbor search, and an embedding matching loss that directly aligns EmbeddingGemma's embedding space with a larger teacher model, Gemini embedding. A notable innovation is model souping with mixture variation, combining multiple fine-tuned checkpoints trained on different data mixtures rather than different hyperparameters to yield models specialized in complementary areas. Matryoshka representation learning provides flexibility at 768, 512, 256, and 128 dimensions. The result is a lightweight model well suited for low latency, high throughput, and on-device applications, an increasingly important niche as embedding models have otherwise trended toward ever larger sizes. OLMo 3, fully open 32B and 7B models. Allen Institute for AI 2 has released OLMo 3, a new family of 7B and 32B open language models with Apache 2.0 licensing, designed to enable the science of language models. The suite includes base, instruct, and think variants, with all code, checkpoints, and training details made public. The 32B model was trained on 5.5 trillion tokens using a staged approach. Initial pre-training on the DOLMA 3 dataset, 94.83% of total budget, followed by mid-training on a mix of web pages, code, math, QA, thinking, instruction, and PDFs, 200B tokens, and finally long context training, 100B tokens. Benchmark results show OLMo 3 32B achieving competitive performance against open-weight models like Qwen 2.5 32B, Gemma 3 27B, and Mistral 3.1 24B across a range of tasks including math, code, MMLU STEM, and general QA. The model is supported in Transformers v.57.0 or higher, with straightforward inference via Hugging Face and options for 8-bit quantization. All revisions for Stage 1, Stage 2, and Stage 3 checkpoints are accessible, enabling fine-tuning from any intermediate point. AI2 emphasizes the importance of full reproducibility and open access for advancing the science of language models, inviting the research community to build on this foundation. NVIDIA's Parakeet, real-time ASR with end-of-utterance detection. NVIDIA has released Parakeet Real-Time EOU 120E v1, a 120 million parameter streaming speech recognition model designed for voice AI agent pipelines. The model achieves low latency, 80 to 160 milliseconds, and signals end-of-utterance EOU by emitting an EOU token at the end of each utterance. It supports only English and does not output punctuation or capitalization. The architecture is based on cache-aware streaming fast conformer with 17 encoder layers and an RNNT decoder. Training data includes a mix of human-recorded and TTS-generated audio from sources such as LibriSpeech, Fisher Corpus, Mozilla Common Voice, and NVIDIA's NeMo ASR Set 3.0. Evaluation on the Hugging Face OpenASR leaderboard in a 160 millisecond streaming setting shows an average word error rate of 9.3%, with strong results on LibriSpeech Test Clean 3.61 WR and Tedlium 5.48% WR. End-of-utterance latency is 160 milliseconds at the 50th percentile and 320 milliseconds at the 95th percentile on TTS-generated Dialog Studio audio. The model is ready for commercial and non-commercial use under the NVIDIA Open Model license and is compatible with NeMo Voice Agent for production voice AI deployments. This release reflects a broader trend toward highly optimized, purpose-built models for real-time, on-device, and agentic applications. Grok 4 probe for semantic drift and refusal onset. A 62-day fixed prompt probe on Grok 4 has been published, documenting 1,242 samples collected to study semantic attractors, thematic inversion, and refusal onset in the model. While the Reddit post itself is sparse on details, the methodology, using a fixed prompt over an extended period to track behavioral drift, offers a window into how large models may evolve or shift in their responses over time, whether due to back-end updates, changes in safety filters, or emergent patterns in alignment. Such longitudinal studies are increasingly valuable as models are deployed in production and updated continuously. The public release of the dataset enables independent verification and follow-up research, contributing to a more transparent understanding of model behavior in the wild. Z-Image Efficient 6B Image Generation. A new image generation model called Z-Image has appeared on GitHub from Tongyi Mai, described as powerful and highly efficient with 6 billion parameters. Details are currently limited, with only the model and an associated blog repository visible. The focus on efficiency and power at the 6B scale suggests an attempt to balance quality and accessibility for users who cannot run the largest diffusion or autoregressive image models. SEC Design Principles for NIM 3.0. The NIM programming language is evolving toward version 3.0 with a new compiler called Nimony, targeting hard real-time and embedded systems with a mostly memory-safe language. The design philosophy emphasizes that if software can run well on embedded systems, it runs well everywhere. Operations should take a fixed amount of time and produce predictable machine code, ruling out JIT compilers and tracing garbage collectors. Memory management in Nimony is scope-based, using destructors and move semantics. The acyclic default means most objects are freed deterministically. Only those involved in potential cycles need the new .cyclic pragma. Error handling is also rethought. The author expresses skepticism of both exceptions and sum-type emulations, preferring to make error state part of objects, e.g., streams in an error state, nan for floats. A new error enum allows raising errors mapped to POSIX Erno, Windows API errors, and HTTP status codes, with the vision that NIM-based services correctly report errors without heap allocations. Nimony's concurrency model unifies async and multi-threaded programming with a single spawn construct, with the decision to run code on the same or a different thread made at runtime by a scheduler. The compiler transforms programs into continuation passing style. Plugins, the final evolved form of NIM's macros, are compiled to machine code, run after type checking, and can transform entire modules. The target release date is autumn 2025. For systems programmers seeking predictability, safety, and expressiveness, Nimony represents a thoughtful evolution of the NIM ecosystem.